Hello, can you all hear me?
Yes, we do. I'm
Okay, good.
making you a presenter at this point, so you should be able to share your screen. Thank you. There we go.
Let me know if it's visible.
We see it now. Thank you again.
Okay. So before I start with part 2 on U-SQL, I would like to point out that the first part has been recorded about a month ago, or 3 weeks ago. So you should be able to watch that part if you haven't seen it yet. Just to give you a quick recap, in part 1, I did introduce U-SQL and talked a little bit about why we have a new language and what the specific characteristics of U-SQL are. We walked through the language philosophy of U-SQL. As a recap, the main aspects there was that U-SQL is very deeply integrated combination of SQL with C# for extensibility that is optimized and processed at the script level and not the individual statement level. We also demonstrated the power and simplicity of U-SQL in terms of its ability to query unstructured data, operate over sets of files, and show how easy it is to use .NET C# to extend U-SQL and looked a little bit at the assembly management. Today, I will pick up where we left off with assembly management. We will be going a little bit more into detail around the metadata model that allows us to manage objects in the context of U-SQL. And then we will take a look at some things that we can do with SQL in U-SQL. In particular, joins, windowing functions, and also recap again the top 5 surprises for SQL users when they come and do U-SQL. And then the presentation will conclude with talking about data scale out with partitioned tables. So this is the scope for today. So let's get started. Quickly, as a level setting again, U-SQL is a query language that we offer as part of the Azure Data Lake Analytics job service. Today it's U-SQL only. We are looking at adding Hive at a later point in time as well. And Azure Data Lake Analytics, together with its other sibling components in the Azure Data Lake, mainly HD Insight and the Azure Data Lake Store, are comprising the Azure Big Data Service that Microsoft offers in the Azure Cloud. So let's start and dive into the matter with the metadata object model. So U-SQL, similar to other relational languages, not only allows you to operate on unstructured data, as we have seen, but it actually also gives you the ability to manage structured data and U-SQL code objects using the traditional metadata object model that you are familiar with from SQL databases such as SQL Server. Now, each Azure Data Lake Analytics account today has exactly one Azure Data Lake Analytics catalog associated with it. And each one of these catalogs contain at least one database plus additional databases that users might create going forward. Now, like in SQL, but unlike in Hive, a database can contain at least one schema. We call it DBO as kind of a historical reference to how the default schema is called in SQL Server. And you can create your own schemas using create schema statements, obviously, as well. Then each schema now contains tables that you can create. Tables are always currently in U-SQL represented through clustered indices. So that means we don't have heaps right now, but only clustered index tables. And these tables can be partitioned, and we will talk about that towards the end of the presentation today. Now, tables can also have statistics associated with it that helps the query optimizer to make better decisions in terms of cardinality estimations and distributions of data to, for example, choose a better join heuristics than if it wouldn't have that information available. Then inside a schema next to tables, you can have views. You can also have table-dwelling functions. You can have procedures. And finally, you can also manage table types that you can use in parameters for table-dwelling functions and procedures. We'll take a quick look at each one of those, either in some demos or as part of the presentation. Then next to the schema, we have C# assemblies. So this is at the same level of the hierarchy as it is in SQL Server as well. And these C# assemblies now, while they have a naming scheme that is basically database name dot user given assembly name, they now provide access to C# functions, C# UDTs, C# user-defined aggregations, and all the user-defined operators. And in that case, we are basically just importing the C# namespaces and C# names so that you can use them directly from within your U-SQL queries. And we'll see an example in a minute when I go and switch over to my demo. Now, furthermore, we have data sources, which is an abstraction that we provide to allow you to connect to other data sources that are not U-SQL based at the moment and are not inside your Azure Data Lake analytics account. At this point in time, these are primarily SQL Server instances running in Azure, so that's either SQL Server inside VM, Azure SQL Database, or Azure SQL Data Warehouse. Now, these data sources give me the ability to expose external tables, and also, of course, I have to manage the credentials that give me the ability to give access to these data sources. So this is kind of the U-SQL metadata object model as we have it today. So let me quickly go into some specific aspects here in terms of naming. As I mentioned earlier, the default database and schema context is kind of following the standard way of naming in SQL Server. So the default database is always called master and the default schema is always called DBO. Now, they are not having necessarily the same semantics as SQL Server in terms of permission settings, etc. It's just that it makes it easier for people coming from SQL Server to kind of know where they are at when they start. We give you the ability to quote identifiers in U-SQL in those catalog names, primarily by using the square brackets. So in this example, my space table is a U-SQL identifier. Now, note that unlike the ANSI SQL standard where you use double quotes for that, we obviously couldn't use double quotes because double quotes in C# are our string delimiters. Now, the actual physical location of where the data is being stored is inside your default Azure Data Lake storage account inside the catalog folder. So all the table data, for example, will be stored in the folder hierarchy inside the catalog folder using what we call structured streams for files, which is the file format that we have been using in the context of Cosmos inside our own big data infrastructure inside Microsoft for the past couple of years. In terms of discovery these objects, you have the ability to look at them either through the Visual Studio Server Explorer, which I will be showing you in a minute, through the Azure Data Lake Analytics portal, or if you want to do it programmatically through the variety of SDKs and our Azure PowerShell commands that we are offering. So at the moment we have the C# SDK, Node.js SDK, and we are currently working on providing you a Java SDK later this spring as well. In terms of sharing, these objects are currently shared within an Azure Data Lake Analytics account. So We are looking at giving you the ability to share across accounts as well, but that's a future work item that might not be available anytime soon. In terms of securing these objects, they are basically secured with the Azure Active Directory principles that you're using to secure, for example, your Azure Data Lake storage account or your job queues, etc. At this point in time, early March 2016, we are securing the objects at the catalog level because we are basically inheriting the permissions from the ADL storage account. Once we get closer to GA, we will be giving you the ability to secure your objects at the database level. Unfortunately, table level access control is something that will be on the roadmap for after GA, and will be probably becoming available towards the end of the year. It's kind of an estimation right now. So let's take a look and look a little bit about shareable data and code. So for that, I'm switching over to my Visual Studio 2013 in this case, where I have my Data Lake tool installed that I can download from MSDN. Now, one thing that you notice that is related to our metadata is if I go over to the Server Explorer and I dive into the Data Lake's Analytics account, and my apologies, this is taking a while because I have access to quite a few accounts here, so it normally takes a while to show that. And let's go down to, for example, my account, and I will be zooming in a minute so you can see it in a little bit more detail. But I want to drill into like some of these accounts here and examples. So now you see within each of my ADLA accounts, I have a list of databases. Now within those databases, you can see I can even have like databases which have weird names. And you will notice that I have here within each of the database, I have a list of assemblies that have been registered, a list of credentials, the external data sources, the procedures, the schemas, the table types, the tables, TBFs, and views. It is similar to the metadata object, obviously, that we have seen earlier with the one exception, which is that we basically pivoted or lifted all the objects that are living within a schema up to the same level as a schema, which is similar to how SQL Server Management Studio is representing the information as well. Now, you can obviously look in and dive in a little bit more. So I can, for example, look at all my tables within, and then I can go into the tables here and, for example, see the columns that each of the tables have, the index that exists, and the availability of statistics if they are there or not. So you can see we have basically a full-fledged navigational experience of discovering my metadata properties. Now let's go over and look at the code. If you remember from last time, I was doing some tweet analysis, and I was at the end using an assembly to contain all the code that I wanted to use inside my custom processing. So in this case, as you can see here, let me increase the font size a little bit more. You have on line 14 this reference assembly. This is exactly referencing the assembly that I've registered inside the master database, inside my ADLA account. And if you look up here on the submit, you will see the Data Lake Analytics account that I'm using with the master database, and then over here, obviously, the DBO schema. So this is the default context in which I run a script if I submit it. So now if I go down here, one thing that I mentioned is that I'm actually using C# names directly out from the assembly that I referenced. So unlike in SQL Server, for example, or other systems, like Hive, where you have to write a wrapper function for every single function and external code that fragment that you want. Because we have this deep integration with U-SQL and C# and the .NET runtime, you basically only have to go and call out to the function after you import the assembly. So you don't have to add additional wrapper functions, etc. That's because we are using C# as the context to do our process. So this makes it very easy for me to share code through the metadata service and assemblies. Now I can go and now also share my U-SQL code here in ways so that I don't have to pass around scripts all the time. And one of the ways of doing that is basically using views and functions and procedures. So in this case, now in my next example statement, what I do here is I create a table-valued function called tweet and mentions table-valued function. What this function does is it takes a path argument where I pass in some default value potentially, and I return a table for the function. In this case, the table has a specific schema, which I'm going to enforce by specifying it here. If I remove that information, then the schema actually gets inferred from the statement. And within this function now, I'm referencing the assembly to bring my user-defined functions into the context. And then what you see here is basically just the multiple statements that I had earlier in my script, now just wrapped up in a nice function that I can use now in subsequent scripts. Now, for those of you who know SQL Server, you might remember that there are two types of table-valued functions. One is a single statement inlineable table-valued function, and one is a multi-statement non-inlineable table-valued function that requires you to basically do insertions into your resulting table type. Now, in U-SQL, because we are already a compositional language that allows us to inline multiple statements and just basically give names, we decided to make our functions inlineable in all the cases and use our function, our expression naming mechanism as the way of returning the results. So in this case, the result address here is basically determined by the last statement that sets the address variable at the end inside the script. Now, one caveat here that I would like to call out, because I've received a few questions on that recently, is these functions are not compiled when they are stored. They are just put into metadata store, and when you refer to them inside a script, you will actually then take those functions and inline them into the script and then compile them. The reason why that is because obviously you want to be able to have the right parameterization being resolved, etc. For example, if I have a path here that is just a simple path, or if I have a path here that is a complex path, the actual compilation of the code might look quite a bit different. So now I can submit this script here. Let me just show you that. To, for example, my Emery's Kona account. So what this does now is it creates it inside the default specified database up here, inside the default schema up here, and creates that function. So if I do the submit here, you will see the familiar job submission. Now this is a job that doesn't actually calculate anything. This is a pure metadata job, so you will not see a job graph here. Instead, you have a tab up here that will show you the metadata operations as they are, as the script has been compiled and executed. So let's see. Compilation has completed, and now you basically see here what were the two operations that we are looking for. Let me zoom in here quickly. So the first operation was that the assert doesn't exist. So this was the making sure that the function doesn't exist, and if it exists, delete it. And then we create the entity, which is basically this table-valid function. And then you see a lot of like additional type information on the side there as well. But if you go back to the job graph here, you will notice the job graph is empty. So now I have registered this function. So let's go back and make use of the function. Now, as I mentioned earlier, we are also providing tables. So what I'm doing now is I could use this TVF now as an abstraction to share with people, but every time they write a query, now they will be still running against the file data and do the extraction every time they are, and schematization every time they run the query. Now sometimes I might want to pre-define the table, taking advantage of the ability to cluster the data, partition the data, have the data stored in its native serialization formats, if it's, for example, numeric data or just not textual data, and avoid having to call the extractors every time. So in that case, I basically can create a table. So what I do here is I create this table. Now in this case, I use a create table as statement, which is basically either create table as select, or in this case as just calling the TVF. Now, as you can see, the function parameter here is exactly the same string with the string pattern, and I create this index now for the table as well. So every table, as I mentioned earlier, in U-SQL currently has to be a clustered index. Has to have within its table, data has to be partitioned according to a partitioning scheme. In this case, I have, for example, here a hash partition on author. Now this obviously is dependent upon what are the type of queries that you want to run over the table most likely, so that you are optimizing your partitioning and your cluster key here in a way that it makes it very useful for query optimization to then have hopefully a more performant retrieval of the data than operating on just the file data itself. So in this statement, I actually create the table, and I not only create the table, I also preload the data that I have from my files. So I can execute this as well and go back to it after it has been executed. So let me find my account and submit this. Okay, it's running. So let me go back to the presentation and do a little bit of synopsis. So we didn't see views, but views are similar to like SQL views. You can say create view as extract or as select. They are primarily useful for simple cases because they cannot contain user-defined objects such as UDFs or UDOs. Views as table-valid functions will be inlined every time they will be referenced. We had table-valid functions, which is the much more usable view mechanism, so to speak, because it gives us parameterization and it gives us multi-statement and even multi-result row sets as well. Now you can see here the syntax makes the table statement optional because in the returns clause, because we can actually infer the result type also from the statement that assigns the result. Now this inference is actually going to be available in the March update, so it's not quite there yet. It should become available in the next week or two. Again, both of these will be inlined. Now, procedures are similar to table-valid functions with two major differences. One, they do not return anything. Instead, you use them if you need to output a result either into a file or into a table. As in SQL Server, you cannot have DDL statements inside procedures. Like table value functions, it gives us parameterization. It can contain multiple statements. It can contain user code. It will always be inlined as well, similar to the inlining that we get in table value functions. Now, table types is a way of enabling me to name a table schema. So I use create type t as table and then give my row information. It can be used, for example, for reuse in function and procedure definitions. So in this example, I have a create function f that basically just refers to the table typed argument of type t. I could also just completely and explicitly give the table schema in the parameter in the function signature, but in this case, I'm basically reusing that type. Today, you can only use table types in function and procedure definition, function signature definitions. In the future, we are looking also to give you the ability to create types, tables of that type as well. Now, we talked about tables. You saw the create table as statement, but we also have the create table statement, which looks very similar to the SQL statement. The main differences are we don't have primary keys or anything like that. The only thing that we give you is the ability to define a clustered index and give you partitioning information. Now, this partitioning information that you see right now here is an internal fine-grained partitioning. That means it doesn't allow you to actually address individual partitions. It just makes the internal data organization more efficient for future processing. At the moment, the only data types that we allow inside columns are the built-in data types only. The clustered index, as I mentioned, has to be specified, otherwise you cannot load data into a table. The current table format is row-oriented. We are working on a columnar format as well that hopefully will become available at some point later within the next half year to a year. The partitioning schemes of the fine-grained partitioning schemes are a few different ones. Hash partitioning, the ability to identify a direct hash bucket, the ability to do partitioning by range, or if you might have highly skewed data and you want to have avoid data skew during processing and have a consistent distribution of data, and you don't necessarily care about the proximity of data, etc., you also have the ability to do round-robin partitioning. Now, as I mentioned, you can also do create table as select or as extract or as TVF. In that case, the schema is inferred from the query, but you still have to define the index and the partition information. So let's go back to our script. And see, oops, I had an error message here in my script. So let's see here. And you will notice that I get schema type mismatch inside my user-defined function. This is showing you actually how the function doesn't really get executed or checked in terms of some of these parameters and so on. While we define it, it's actually being checked when it's getting used because of the inlining characteristics of these functions. So in this case, it looks like that I have a type int, but the actual type is long question mark, and so therefore the result that I'm getting here is actually wrong inside my table divided function. So if I go back here and show you the function, I did say here that the tweet count is int, but it actually needs to be long question mark. So if I go and change this and then save it and resubmit it, you will notice that at that point in time it will work. Okay, so now let's switch over and do some analytics. In this case, and do some SQL statements with it. Here in the TDF, you might have noticed down here, when I pivot my individual mentions that I have, potentially many per tweet, into one mention per row, I'm basically using a cross-apply statement down here. So the cross-apply statement is a statement that is familiar to people that are familiar with SQL Server, obviously. Although in this case, since we are not giving you the ability to cross-apply with table-valued functions or subqueries, we are currently only give you the ability to cross-apply with a limited set of functions that we support and some C# expressions. Basically, in this case, explode is a built-in function that takes an array and pivots the array into one row per element inside the array. For people that are used more to high for the ANSI SQL standard, cross-apply basically corresponds to the lateral expression in those languages. So now let's look at some other tweet analytics here. So the first thing I want to kind of take a look at is I want to look at my function, at my tweet and author and mentions, and for each of the categories for the author, I want to take a look at what is the overall 50th percentile or median value for each of the categories, basically. And then I want to see for each author, how do they rank in the category with respect to the tweet count, both as a relative rank, which means I see the percentage where they are at, and as an absolute rank, which is the actual position within it, to see where they are at in terms of the position. Now I do that only for tweet count greater or equals 50. As you look at this closely, you will notice this very much is basically SQL windowing functions. So nothing surprising here. Now, if I go down and take a look at the next thing. So now I would like to do something else. I would like for each author who provided their tweet feed for my analysis, meaning that file that you've seen earlier that I was doing to operate over extracting my data. Now I would like to see how influential they are. Now, how do I define the influence? The influence is basically the number of times a person got mentioned divided by the number of times a person tweeted. So that means the more the person gets mentioned and the less the person tweets, the more influential the person is. So now one thing I've noticed inside my data set was that some people, including me, have changed their tweet handle. So while I might be still being referenced with my old tweet handle when I'm getting mentioned, obviously all the data that shows that I'm tweeting, where I'm the author, already has been updated by the data. But now I need to do some cleansing. So what I'm doing here on line 32 is I basically define a table of constant values, which allows me to map my old handle to my new handle. And now how do I clean the data? Well, I do a left outer join here based on the author and the old handle. And then within my select statement, I check if a new handle exists. And if it does, I take it. Otherwise, I take the old handle. This is a C# expression, which is basically similar to a null if in that sense. So this is basically the cleanup. And now the next thing I do, obviously, is I now need to start doing a self-join. Now I'm currently only looking for the files for the authors that have provided me the file. So I'm using this file origin array and check that the author is indeed inside that. And then I do a group by to get the tweet count. And then in the next statement down here, I do a self-join. So I can join my mentions with my authoring, and the influence factor is calculated here. So as you can see, we have a lot of standard join expressions that we can use, and we can even do self-joins. The joins can be done between tables, such as up here. They can be done between calculated row sets, such as down here on line 54, or they can even be done by data that got extracted out of a file, which is not quite visible right here, but you can imagine that this is just another row set expression. So this is basically the ability for me to do joins and other SQL statements. So let's recap that quickly. As first, let's recap the cross-apply. So the explode, as I mentioned, takes an array and then basically pivots each one of the values inside the array inside a row. We have the same expression also for maps, except for that it gives me back two columns, one for the key and one for the value, and then have a key value pair per row. Now the cross-apply, as in SQL Server, is taking now this table-valued expression and applies it to every single row inside my input row set. In terms of the joins, we give you all the familiar join operations. So we'll have inner join, left, right, full outer join. We give you the ability to do cross join. There is also a semi-join operator, which gives you equivalence to in with subquery. We also have an anti-semi-join operator, which is equivalent to the not in subquery. There are some caveats around joins. In a scale-out environment, there are no efficient algorithms for processing general join algorithms. So in the worst case, you will always have to do a cross join and then apply your predicate after you basically do the full composition of all the data. Now, there are efficient algorithms for doing equijoins and joins with and conjunctions of equality comparisons. So therefore, we basically are currently forcing you to think about how to formulate your join by having some syntactic constraints to make sure that you know what is efficiently executed and what might be a little bit more expensive in execution time. So that means that the on clause inside your join always has to be an equijoin or an and conjunction of equijoins. And they have to be simple columns. Now, if you have an expression inside it, so you want to do some calculation on it before, you can do that. You just wrap it into a column in a previous select statement. So it's doable. It's just you have to go and do that additional step. Also, if the comparison operation is not equals, you put the comparison into the where clause. Now, if the join does not have any equality comparison, then it's a cross join with the predicates inside the where clause. And again, the reason why we currently do that syntactic restrictions is that it makes you aware of which syntax calls are and which joins are able to be executed more efficiently than others, so you kind of have a feel for that. If it becomes too much of a burden for people to write it, rewrite it themselves like this, at some point we might be considering to relax the syntactic constraints and do that for you. But I think right now, my feeling is it's much better for people to get an awareness of, for example, that an equijoin is going to be much, much better than, let's say, a predicate that does a between. We already mentioned and saw some examples of windowing expressions. We have the standard over windowing expression that you might be familiar with from SQL Server and may love or hate it because it's not the easiest syntax and expression to remember and learn. In terms of the windowing function calls, we give you the standard gamut of aggregate function calls, analytic function calls, and ranking function calls that are that are listed here on the slide. Lead and lag should also become available in the next update in this month. And you can see basically these are the supported functions. Now, like all the other scale-out environments, there is one caveat that I have to raise here, which is that if you have a large data skew where you have a single partition inside your windowing function that is bigger than the amount of data that can be processed in a single node, at that point in time you might get an error message, and you will have to basically repartition the data and do your windowing function in 2 steps instead of in 1. So having said that we do SQL, let me just quickly give you a summary of the top 5 surprises for SQL users. The first one is that we are case sensitive. So as uppercase is not the same as lowercase. The reason why that is that we are combining SQL and C#, both of which have keywords that overlap. And C# is case sensitive, so we basically did take a look at investigating if we could make our U-SQL keywords case insensitive, so you can have lowercase select and lowercase s, etc. But it turned out that making this happen inside our compiler framework was very costly, was probably about 6 to 12 months, person months to get that done. So we basically decided to better build capabilities than tinker with the syntax. So if people are very passionate about being able to write camel case select statements, please let me know, and we will be eventually investigating whether we can spend an amount of time to make the parser case insensitive. Also, equals is unequals equals equals. In C#, equals is an assignment operator. So all the predicates that you write in U-SQL have to use the C# comparison operation, which is for equality equal equal. Null is not null. C# null values are, unlike the SQL null values, 2-valued, which means that a null is always equals a null, and not null is always not equals anything else but not null. So, which means that you, unlike in SQL where you have like the unknown third value in comparing nulls against something, we can always tell you that whether something is true or false. Some people like that, some people might have issues with that, but this is the C# semantics that we are inheriting. Also, while you have seen that we have procedures, note that we do not have standard procedural control flow operations. So we don't have currently a statement level if, although that's currently being worked on. But we are also not having any looping constructs where we basically would take a look at a value that we calculate and then do further loops around that. The reason why that is basically that there is no efficient way of doing that in terms of optimization of our script plans. So therefore, if you need to do a looping, you basically loop outside. So you write an orchestration layer that calls the script until the looping condition has been achieved. Also, or if it's on a scalar level, you basically move it inside your custom code. I mentioned that we are an append-only store, I think last time. So, like most big data systems, at least up until recently, they are append-only. So you can do insertion, but you cannot do updates or merge or individual row deletions. If you need to do that right now, we require you to do a transformation, meaning that you filter out things and then recook the resulting data structures as part of a script instead of doing an update or a delete statement. However, as I mentioned, we can do insertion. So let's take a look at an insert statement. And as you can see here, the insert statement again follows mostly the SQL familiarity of doing inserts. So you say insert into, and then you can say insert into select, or in this case, I say insert into values. And I can give multiple rows here as my statement. One of the things I want to call out, though, is that because of the type system being C#, we are basically having a very strict C# type checking rule. So if the schema of the table, for example, is not a long question mark, so one L here is a long, it's not a nullable long, I actually have to do a cast. The same goes for null values. Null values are not associated with a type, so I have to say of which type the null value is before I insert it. So this is just a simple insert statement. If I go back to my demo here, to my slide deck, you obviously have seen how to add insert constant values. I can also insert from queries using the standard syntax. And I can do multiple inserts into the same table. So I can basically incrementally append data to my table as time goes on. Now, there is an issue there with it, because the internal file representation of a table is basically a sealed file that you cannot open up without a lot of pain, etc. Any insertion that you're going to do, any insert statement will create its own file in physical storage. So that means if you have a big file that you created with your create table statement with the first insert, and then you're adding additional data, for every insertion you're adding a new file. Now, having additional files obviously will be degrading your query performance over time, because you're losing the clustering, you're losing the partitioning at the global level. And so eventually you want to basically recook the data. Now, the first recommendation here is obviously trying to avoid small insertions. Single row insertions are bad. However, after a while of maybe even doing daily insertions, you want to recook the data, rebuild the data after frequent insertions. And that's being done with an alter table rebuild statement. That statement, again, I think might be already present, or if not, it will be present after the March release. So let me now start with the last topic, which is my scale-out story. Now, for that, I'm going to use a slightly different data set that I have been using to show that, which is basically some form of vehicle telemetry data. So what I have here is I have a schema for a table that contains for each vehicle ID the date on which the event has been measured, so meaning at what date I actually measured the vehicle telemetry data. And then there's the telemetry data, meaning where was the vehicle at any point in time, what was the speed it was traveling at, what was the direction, and which trip ID was being recorded as the trip that this vehicle was doing. So in this case, it's actually a mocked up ambulance driver. So each ambulance driver, basically every time he goes on a trip, has a trip ID associated with it. Now, this table now is going to be partitioned in 2 levels, because I want to be able to manage my individual partitions based on event date. So how do I do that? Well, I still have to define a clustered index. Thank you, Paco. I think we will be done in about 5 minutes. So you will have the ability to, or you still have to define the clustered index, but now you have, your partitioning is at 2 levels. So in this case, I still have my hash partition. In this case, I basically partition my vehicles IDs into 4 hash buckets. But now I'm also creating individual date-based coarse-grained partitions using event date. Now these, currently the syntax is buckets. We are going to clean up this syntax before we go into GA to make it a little bit more consistent with some of the other partitioning languages that we have around SQL data warehouse, etc. Now these buckets or these coarse-grained partitions are actually individually addressable, meaning you have to create them explicitly, but you can also manage them explicitly, recreate them explicitly, query them explicitly, etc. So let's take a look at how that works. Well, in order for me to create a partition, I have to create the value for the bucket partitioning. In this case, because event date is a date time, I'm using a date time value here as the partition value. Now, please note that you should obviously make this value not too coarse-grained, because otherwise you're ending up with single row partitions. In this case, I decided to do it at a daily level. Now, also note, in order for me to have the right kind of consistent viewpoint on the date time value, it has to be datetime kind.utc. So then what I do is I have 4 event dates that I have here, September 14th to 17th, 2014. But first, I just create 2 partitions for that table. So I have created the table. Now I'm adding 2 partitions to it so that I can start inserting data into it. So how do I load the data? Well, in this case, I have data, again, using some file stream syntax here that I'm extracting from files that have a date given as part of their file name. So that's what I do here with this extract. Is I basically extract the schema information with all the date information, including the event date here, from those files. And then I'm inserting it into this partition table. Now, one additional clause on this insert statement is basically telling me what should I do if my row set that I have up here contains event data that is not available as a partition. Currently, we have 3 options. One is that we error. Another one is that we basically just ignore the values on if we can't find the partition for them, which is basically what this statement does. And the third one is that I can actually insert the data into a specific overflow partition for which I have given a specific event date name, which I then can specify up here. So as you can see, in this case, I insert 3 dates, date 1, date 2, and date 3. But I only have created my partitions for date 1 and 2 up here. Let me see that up here. So that means all the values that I insert for date 3 are basically now just being ignored. Now I add another day statically. So I can now, for example, through incremental daily inserts, I'm adding a new partition to my table. And then I can insert directly into that partition of that table. Now, obviously, since the partition information already gives me the date for my event date, I'm not specifying that inside my select clause now. If I would get an error message. So this is how I create partition tables. I can create them either explicitly with adding a partition, inserting directly into the partition, or have it automatically routed. And then when I query it, I basically now just use my standard SQL statements here. Select star from, here for example an event date, group by. And down here I give a predicate. In this case I'm giving a having predicate on the group by, but I could also give a where predicate. Now these predicates are actually being evaluated by the query optimizer, and you will get partition elimination. So that means if you have one of those coarse-grained partitions, then and your predicate is clear enough to know for the query optimizer that it doesn't have to look at that particular partition, then that partition will be disregarded. So let's summarize this. As I mentioned, you can create partition tables. That's done by this bucket statement at the moment. You create partitions either by basically saying alter table, add partition, and then you load data into the partition either dynamically or explicitly by giving an explicit static location. If you query, you will get partition elimination. Coarse-grained partition also is very useful if you want to drop old partitions, like data is expiring after some time, you want to delete it. Then you can delete at a partition level. Or if you have to recalculate data inside your data table and you want to only recook partition level, then you can do that as well by basically truncating a partition and then reinserting it into that partition. So let me quickly finish here by basically calling back to action that you guys should be joining the public preview if you haven't done so already. Sign up for an Azure Data Lake account. We are currently whitelisting accounts for our public preview, and give us feedback on either how you like it or what you think you would like us to see to add. I think U-SQL really is very easy to use and gives us the benefit of the SQL declarative experience together with the C# extensibility and being able to operate over both structured and unstructured data. Additional resources are given here. That includes usql.io, which is the pointer to our GitHub page, where you will find the two sample projects, the Twitter data analysis and the ambulance data, in the GitHub repository. There are additional documentations and slides, etc. If you go to slideshare.net, you will find also, for example, some slides I've presented on optimizations and other things. So you can go and take a look at this there. And then we are basically monitoring our own ADL feedback page on the Azure User Voice, MSDN, obviously, and Stack Overflow as well. Items that I haven't covered yet are how to use UDOs, how to use user-defined types and user-defined aggregators, how to use resource files and other runtimes in conjunction with your custom code. For example, being able to run a Python script as part of your SQL user-defined function. And I haven't talked about federated queries against SQL databases yet. That might be a future presentation that we might want to do at some point in the future. Thank you very much for your attention, and I think we might have